Okay, I think it's time to start. We would like to welcome all of you in this week's seminar for the Center for Informatics and Computational Science. We welcome Leonardo Duenas-Osorio from Rice University. Leonardo did his master's at MIT, and he got his PhD from Georgia Tech. Broadly, he's working on infrastructural resilience with emphasis on computational methods for the lifetime performance assessment of structural infrastructure systems. He holds a couple of important positions in different groups within the American Society for Civil Engineering. Most importantly, he's chair of the DAS group of risk assessment of structural infrastructure facilities and risk-based decision making. And his talk today is going to be titled Towards Guaranteed Reliability and Resilience Computation for Complex Networks. So let's welcome our speaker.
Well, thank you, Alex, and good afternoon, everyone. Let me also thank Nicholas for the kind invitation. I am very excited to be part of the Center's series. And looking at the list of speakers for the year, I got nervous when I saw all those luminaries coming out. So I hope there is topics for all of you here. What I'll be talking about is sort of a new movement in engineering towards estimating properties of complex systems, but in a way that we can guarantee the quality of what we say. And let me get started then with a, something happened here, okay. With a quick motivation, engineering reliability and computational thinking have been really linked since several decades ago. We have solved very challenging problems like human spaceflight problems, nuclear power, lifeline systems like power. This is actually me in Chile after the 2010 earthquake in a ultra high voltage substation. But what is common about all these systems is they are complex in the sense that they have too many components, each designed with different, let's say, standards. They are subjected to natural hazards, and in the end, we as engineers have to specify how they should be designed so that the risks of failure are still acceptable. And obviously, this has gone with, you have seen, we have also have tragedies with many of these complex systems. But nonetheless, the computational part has been what has enabled progress, and we'll see from fault trees to Monte Carlo simulations and the like. But nowadays, if we fast forward and what we anticipate, we have other kinds of systems that are becoming perhaps more complex. And I have just two examples here because they relate to work we do in Houston. Smart cities, deep space habitats. These are emerging complex engineered systems, and they are emerging in the sense that they are more interdependent. Their subsystems are more interactive. They are more autonomous. They are data-driven. They are more adaptive. And when we have to ensure the safety and reliability of these systems, the problem is more complex because now we have human artificial intelligence interactions there, and yet we have to ensure that they perform as intended. So our community, through many agencies like NSF, NIST is the agency that is in charge of the standards and technology, Department of Energy, Department of Defense, they are spearheading the notion of community resilience, which sort of captures these new systems that we see, where we have advanced infrastructure systems, where the users are part of the system, and where the reliability and resilience are by design embedded in them. Resilience means that if something goes wrong, we can get back to our feet as quick as possible. So we see here reports. I just put some reports from the National Academies, from the state of New York, from NIST, but there are many others. So they are putting the money in their mouth, or however the saying goes. So as an outline, I have 4 parts here. I'll give a quick sort of rundown on how we do engineering reliability today, mainly. Then some taste of some methodologies that are very algorithmic and successful at solving some problems that otherwise were thought to be difficult. Then similarly, methodologies to solve the resilience problem in a way that offers quality of guarantees on the quality of the estimates that you provide. And then the last part, part 4, is where I hope to spend a third of the lecture, is on the new directions that we have. Here we are leveraging topics from computational logic, from quantum computing, to solve problems that hopefully relate to these emerging systems. So, as a way of getting us started, one object that we can think of that is part of these complex systems of today is the utility systems or lifeline systems. They are all interdependent. They are large scale. They have a variety of failure modes and aging issues. And they are evolving more into this hybrid human-AI operation. And yet, we as engineers have to ensure that they are working all the time. In fact, most of the time they work, that's why we don't notice them. If we notice an outage, that's a rare event nowadays. And it's not the same in every country, but at least in North America has been that way. But the problem is, as this automation comes in, we are running out of methodologies, computational methodologies, algorithmic thinking to actually certify if these systems are going to perform as intended. So within the computational realm, the first thing we do is realize how problems that we are interested in map into computational complexity classes. Those are useful mappings so that we know what can be done exactly and what is going to be hopeless because the instances, as they grow larger, they are going to be not computable, so we have to approach with approximations. And we see reliability here at the top is one of the basic definition. Reliability is the system will perform as intended. And it happens that it's a sharp P problem. Sharp P means that it runs in exponential time. And we have similar problems like redundancy, robustness that could be mapped into reliability. So they are equally expensive from a computational perspective. And there are some special cases where we can solve this otherwise expensive problem in actually polynomial time. And I will explain that, and that's sort of some of the recent contributions. It's a special case, so it's not a panacea, but it gives a taste of what it is. And then we have bigger problems like resilience. I mentioned resilience, getting back to your feet despite some failures. And here in this sort of bubbles size is bigger because the problem is computationally even harder. And it's harder because we have now decision making in the mix. That's where the human or the AI system is making decisions, and therefore your state space just grows even larger. But if we know that our problems are in that category, then we start from some solid ground pursuing approximations that are principled. So let me give you an example to provide some background here. A textbook example, literally textbook example. They're in the Texas Gulf Coast, or hydrocarbons. So we have petrochemical facilities. One typical problem is you get oil and gas, and then you want to separate the gas from the liquid. In reliability, we want that tank not to explode. And that's a typical problem. That's something that people are concerned today. So what do? To ensure reliability, we just put stop gaps. If something goes wrong, then we have some safe approach. If that goes wrong, then what else can we do? So here, if the pressure starts going up for some reason, we have some pressure devices valves here that will close, but they will close only if the pressure switches are working and they measure that some overpressure is coming. There is a logic unit here that must be working. If all that fails, we still have some predetermined pressure escape valves that they will pop, and there are two of them just in case one don't work. If all that fails, there is a rupture disk here that is going to pop before the entire tank, and if that fails, then you are toasted. But that's a common example of what we want to compute and therefore design so that we don't get into trouble. I'm bringing here this picture because this is one of the most successful techniques in engineering reliability called fault trees. And I bring it because it has a very computational flavor. It's full of logic gates, ors, and ands, and you in a logic sense have at the top an equation that will tell you are going to be in a failed state or not as a function of the individual variables. Individual variables are the smallest units that could fail, and their combinations is captured into what we call a limit state function. Now, that limit state function becomes not available in explicit form for larger systems, because you might have then a very high dimensional problem. I have here 8 random variables, but you might have thousands, and therefore you might not be able to get the equation. Or most likely you don't even have enough understanding of the system in a stochastic sense to even come up with that equation. So what do we do today? So I'm talking in practice, and we do Monte Carlo style simulations where you have a computational model of your system, and then you have input random variables, again, high dimension. I'm just showing 2 here because we are constrained here in the board. But you do experiments, and then you see that some combination variables are safe and some are not safe. And if you do enough of those, you might identify that there is sort of a failure surface there that delimits the 2 domains, and that becomes your limit state. You can learn that limit state function from physics, from these computational experiments. More recently from machine learning, because some of the time the limit state functions are actually weird in shape. They have multiple points that can lead to failure. So I'm here just showing an example again in two variables. That limit state function could be almost anything. This is food for thought. Machine learning is really bringing some insights into trying to approximate or where to sample so that you can reconstruct these very complex failure domains. What we need to is what is the principal methodology to bring that and again guarantee results. Now I bring this as another methodology that is standard in our community. It has a tradition. It's called the first order reliability or second order reliability, where you linearize or approximate to a second order degree your limit state function if you happen to know it or if you have learned it from some data. But then once you have a surrogate model, then you can do the uncertainty quantification more cheaply. So that's what is done today, mostly. But what is the problem with that is that none of those give you ahead of time a guarantee of the quality of your estimate. They will not tell you what the error and the confidence of your estimate is going to be. You can obtain that as you go, but not ahead of time. And it seems with the systems that are becoming automated, we need to have those certificates ahead of time. We cannot wait and see because it might be too late. So I'm going to show one methodology that's sort of inspired by that, and it gives an idea on how computational thinking start helping other fields and with the necessary adaptations to your own discipline. So I'm bringing here the combinatorial Boolean approach. Boolean logic is really at the core. It's almost like the currency language. It's a fundamental language that then we will use and leverage for many other applications. It's like when we were learning computing, it was the DOS or whatever primordial way of coding. Boolean logic gives you like a very fundamental way of describing problems. So here, let's say I have a system that has two components, and each component can fail or not. So they are in a binary state. And if you expand all possibilities, since it's two-dimensional, you have four possibilities. Both components in, or this bar indicates a negation, so both components out. So if you understand your system, you know what they are. You can ask what is the probability of having any failure or both failures. So as you may imagine, when we have more components than two, the thing grows exponentially. So we have actually started exploring this successfully for some renewable energy. This is a very engineering problem today. Texas is now leading in wind energy in the nation. It used to be California, but now it's Texas. And here I'm just putting three components. These machines have hundreds of components, but I'm just highlighting three: gearbox, electrical system, generator. Well, if you have three components, the power set of three components is going to be 8 configurations. Again, none of them working, all of them working. And you might be interested, what is the likelihood of any two of them working or any one of them? And here I'm just highlighting the subset of all configurations in which any two components are up or down, depending on your Boolean. So you can actually write an equation for computing the probability, let's say, of two elements, any two elements working. And the equation, what I want you to recognize is just sum of products, which is a canonical form, is sort of the canonical form of a reliability polynomial. And what it's doing is the product is the product of the state of the components, and we have in this case 3 of them, and they are mutually exclusive, so we add them up. So it's like a nice bean counting approach. This equation is also the same as in other fields, like the partition function in physics or statistical physics, or Potts model, or in computational sciences. It looks very much like a CNF Formula, disjunctive normal form, sum of products. So if you ask the combinations for, more generally, for any no component or one component or 2 components or 3, well, you get just the general formula, and it's expensive to evaluate. So it will naively evaluate to 2 to the n. So the first insight that I wanted to discuss was, well, in just number theory, or just it's known for centuries that you can express the binomial coefficient recursively. And we know that the power set, the combinations, they relate to the binomial coefficient sum. So why not extending that, which this is at the scalar level, why not extend it to a set level? So that sort of a small gave inspiration to a recursive method that helped us solve the reliability problem under some assumptions. Here I have the expansion for 3 components, and notice that the subset where every 2 components fail shares something with the subset of every 1 component fail. They share a core. They do differentiate by some specific sort of multiplier that we can correct for. And then we have to do only 1 computation. So I can use computations of higher order by relying on prior order, just recycling results and then just doing a few. And this computation becomes now n squared. So it went from 2 to the n exponential time to n squared polynomial time. This is the smallest polynomial, of high degree, the high in quotation. But what is the catch here? That we surrender statistical correlation. So here the core assumption is that the failure of the components are all statistically independent. Yes, it's a major assumption, but at the same time, it gives insight. The moment we put correlation back, the recursion breaks down. So it gives insight into how correlation becomes this, the crux of computational complexity for this class of problems. You can go from polynomial to exponential by acknowledging correlation. So that's an interesting thing, and we have applied this for the wind turbines with 12, 24 components. The moment you start adding about 30 components, if you do it naively, you cannot do the computation. But with this, you can actually do it, and the fact that you have this combinatorial nature, you can elicit other information, like what components contribute most to which configuration. It's like you have some byproducts there for sensitivity. So let me see if I have. So I have here just a chart to conclude this part where a little bit of, again, computational thinking helped with a very practical engineering problem. And here bounding, if we have components up to 17 for this chart, the recursive method is this green line, the general combinatorial is the blue line. Those are exact sort of bounds. They will provide exact numbers under the assumptions that you have. The recursive under the assumption of no correlation. The general one. But then we have a huge span here where anything can happen, and that's where the simulation comes, and ideally simulation that has some performance guarantees or principal approximations. So we'll get into that in a moment. But before that, I want to show also some of the sort of interesting methodologies to solve the resilience problem. So the resilience problem is now you have your system and something went wrong, and you want to restore it as fast as possible, meaning also with the minimum cost. So you have an optimization problem there. And given that the components are binary in nature, we have some mixed integer programming. Those are known to be hard problems as well computationally. So what can we do? This is just the equation. So what I want to highlight here is that there are multiple components that we want to optimize for. And we want to minimize the cost of preparing the repair. This is a very engineering-driven objective. You have to go and dig in the road, and you don't want to repair twice the same road. You might have seen that happening. We need to reconstruct the arcs, the nodes. We want to not have oversupply or undersupply, and just typical flow costs. The many subscripts are the elements, from I to J. K is the layer that you are dealing with, and T is for time, and you can have additional things. So you are optimizing this, and you have a variety of constraints. I'm going to skip the constraints because there are too many, but there are typical constraints for network flows if you have taken operations research classes or network flows. But more importantly, the constraints are going to be in resources that you have available, interdependencies. Some things need to be repaired before others. So there are very naturally inspired constraints. And what happened is, this is one of my students, when you put the constraints matrix, it's all fuzzy, you don't see anything, but then he had the patient to kind of group things, and these are actually all the constraints related to flow variables for one system for the other, or for two kinds of variables, interdependent or not, functionalities, and you see labels there. Bottom line here is that we realize that for the interdependent problem, we have a block diagonal structure where many of the constraints are kind of their own box. And then you have, yes, some coupling constraints because of the interdependence, but they are not too many. And therefore, we can decompose this using some decomposition method. We started with dancing wolf decompositions, Bender's decompositions. There are ways in which you just solve the blocks and you keep track of the couplings, and you can solve to optimality. I'm mentioning this approach, the mixed integer problem, because if you solve it, you know that you have a guaranteed optimum. It's not a heuristic. We tend to use in our field a lot of heuristic optimization methods. They are good to explore, but again, you will not have guarantee that you have achieved the best. And with systems that are being automated and that you have low time for contingency analysis, I think certification of optimality or quality is necessary. What was interesting here is that we saw that structure, and then we say, well, this is for a given time. So you have the system, it gets damaged, and the optimizer will find the best next things to repair to bring it back. But what if we account for all time? So now you get a bigger problem. So the small problem is a block diagonal element of a bigger matrix, where now you have as many blocks as time steps. So now you're solving a bigger optimization problem over all times. So you are sure that you are finding the best solution for the restoration time of your problem. And then you have variables, the ones that couple and the ones that you have to deal with. Then we realize that we need to bring a little bit of the uncertainty, because that's part of the motivation for all this. So we now take this previous problem and put it as a block diagonal of a modern matrix here, that now every one of the blocks is a scenario that brings the uncertainty to the problem at hand. And you can, again, by this decomposition algorithm, solve it. And solve it in practice. We have solved it with commercial solvers, Ciplex, Express, Gurobi. Some of them have now the L-shaped decomposition, which is good to, they automatically detect this sort of block diagonal structure, and they will, so they are very efficient, very fast. But eventually, if your problem is too large, you are not going to solve it. Some example application, NIST and NSF have been big in test beds or showcasing some applications. So here is a quintessential test bed for us. This is Memphis or Shelby County in Western Tennessee. Earthquakes are likely there. Not as frequent as we know from the West Coast, but they are likely, and the risk is great. So let's say we have a potential earthquake in the New Madrid seismic zone, and we have utility networks like water, gas, power, and here is just an overlap of some of the underground networks like water and gas. So you have the data for those. An earthquake might happen from that New Madrid seismic zone. You have a damaged system of systems. How can you bring them back? Then you bring that optimizer. It will tell the sequence of repairs and the cost. And here I have the results. So here in the left, for many of the scenarios, seismic scenarios, you have sort of the average restoration. Here is the systems get the event at time 0, and then they start getting better as time periods. Time periods could be half days or 1 day. It's just a time step in our algorithm. But what we see here is that these optimizers guarantee optimality for many of the scenarios, and we get bounds as well. We see the worst we have done or the best on average. This is when we have systems that are strictly balanced. Basically, you have enough supply to satisfy the exact demand. In general, we have a buffer. So if we have a buffer of 10%, in fact, for electricity, we need to have more than 10%, and most states comply with that. Some of you are doing electricity markets, you might know on that. But if we have a little bit more of that wiggle room, then the optimizer is designed for that. So it finds very quickly the restoration strategies for a variety of scenarios. Then to show a little bit of the merit of this stochastic information, we have something that we call here the value of stochastic information, basically comparing with what would be a couple of ideal scenarios. One is actually an ideal scenario and a practical scenario. The practical scenario is we tend to optimize, when we have uncertainty, we tend to optimize for an average sort of future scenario. An average scenario that will capture the variety of the uncertainty. So if we optimize for the average, but we solve the stochastic program for many earthquakes on that Memphis, we see that, yeah, we solve and we have just some outliers. These rates are outliers, but on the average performance, we are pretty good. And then on the other extreme, I'm bringing that if you have perfect information, which we are getting there, We aspire to get there, but perfect information is now you have sensors deployed. This goes with the concept of smart cities. Sensors are a way of bringing perfect information at the time step in which you are, in the sense that you know exactly what is the state of that element, or if you have water or not. Or so, if you happen to have perfect information in all components, then the optimizer just flies. It just finds the best solution, and these are all efficient and the like. But again, for systems, these systems combined, we're on the hundreds. If we are on the thousands, we cannot solve this anymore. So we have to, same with the previous example when we add correlation. When we try to make them more realistic, either bigger or with correlations, even though exact or guaranteed optimality, they break down. So what else can we do? And that was our conundrum. So that's where these new directions come in, and I hope to spend 10 or 15 minutes maximum on this. But this is sort of the new developments, and I hope this triggers discussion. So one of the things is, with some of my colleagues, we got inspired by success in other fields. I studied at Georgia Tech, and the traveling salesman problem, TSP, happened to be at Georgia Tech big because they have a code called Concord, and it was the world champion in solving TSP instances. Now, TSP is a problem that is computationally hard. It's one of those NP hard problems, meaning that naively you cannot solve anything too big because you just run out of time and patience. But they are solving, last time I checked, it was about 70,000 nodes. And the traveling salesman problem is finding the shortest sort of route to connect every link once and come back if you have a circuit. So they are doing 70,000. But this is supposed to be an NP-hard problem. Then you look under the hood, and they are exploiting every possible heuristic to warm up the problem. They understand the idiosyncrasies of the TSP. So there is a lot of, here is where the algorithmic thinking comes, and the domain-specific knowledge comes. They combine in very clever ways to solve practical problems in reasonable time. More closer to our needs, which is our elements, again, in a reliability problems, the elements fail or not. They could have intermediate steps, but in general, you are interested in fail or not. So there is another big problem called the satisfiability problem, SAT. And it's naive. The satisfiability problem is you have a bunch of variables. They can be assigned true or false, and they are related by ORs and AND gates. It's like a fault tree. Remember that when I began and I said this relates? Well, a fault tree, if you write the formula like a Boolean formula. And the idea is to evaluate which combinations make the formula true. True being safe, true or not. Well, in a naive way, you just do a binary decomposition. So every variable is up, and then every other one will be up or down, and this just grows exponentially. And yet, the people in SAT are solving also tens of thousands of variables efficiently. So, what is this? Again, you look under the hood, they have a lot of understanding of the problem, like direct clause, conflict-driven learning. It's a lot of heuristics there, but in the end, they drive the process, and you find solutions to large problems. So here is where we realize the nature of a logic tree. In fault trees or in SAT, it was the same. If you abstract them, it's the same. So why not finding a way of mapping things and leveraging so much knowledge from the logicians in the last 20 years or so? So people actually call it the SAT revolution. And here I have an example. So now we have a network. This is a small network. And instead of nodes, calling them nodes, I call them clauses, because a clause is basically one of those collections of literals. Literals are the variables. And for us, the variables are the links of a network, and the clauses are the nodes. And a clause means that you have some logic operator there that is going to be true or false depending on the values of the variables that are incident to it. So this brings just the graph notion of representing infrastructure networks, the graph theory basics. But now every clause is a logic sort of formula, and you can write it out. So here we have 4 nodes, so you have 4 clauses. Every clause has 3 variables, so you have them there. They are the links incident to the node. And since this is written in a conjunctive normal form, this is basically an OR of ANDs. So that's the so-called CNF formula. So you can evaluate this formula efficiently, even for thousands of variables, if you have something like that. And not only that, but you can count how many solutions are actually okay. But this problem, as formulated here, doesn't solve the reliability problem. It's a simpler problem. And I call it EC, and I have an example here. The EC is the edge cover problem. It's a simpler problem that is, the formula is specifying the combinations in which the nodes are never going to be orphan. So what combinations of links you need so that the links are, the nodes are always connected to something. So this is a very small configuration that satisfies that sort of formula. Having link 1 and link 5 satisfies my criterion of whatever you want. Now for reliability, we want at least full connectivity. That's one of the goals. That's one of the manifestations of reliability, is that you can, in principle, connect every node with every other node. There are many other definitions, but that's, so the formula gets a little bit different. Or there is a formula at all. So that's the thing. So for a simpler problem, the edge cover, the reason that we can write the formula is because it's local. Notice that I can satisfy this independently of what is going there, but if I satisfy that, then I am satisfying globally. So we understood, you have to learn the ropes of the other fields, that, okay, this is a local problem, and that's why there is a lot of success. When you have formulas that have this local nature, you are very successful. What happens when the formula is not local? When you have a global property like reliability. So for reliability, I'm putting in red, this is a configuration that satisfies reliability, because now every node can be connected to every other node. There are many other ones, but can you specify a formula? What we realize is that specifying a formula explicitly would be solving the reliability problem in the first place. So it was no good. We realized then that there exists some family of formulas that actually have an existential quantifier. And what it does is, you have a formula that you lifted into a higher dimensional space, you have more variables there, and all you are saying is there exists some variables of this combo of links that you care plus new variables, and they will satisfy that formula in that space. And then you project down what you care about reliability, which is only on the links. So you lift links into more variables, you check for solutions in that higher order space, and then you project back only on the solutions of the links. What happens is there are many solutions in this higher space, but you just project the unique solutions, and those become the solution to your problem. So that was an insight that really just happened by working with computational scientists and engineers. It would have not come otherwise. It was that collaboration and thinking together. So what it has this formula has that existential quantifier that it says only there exist some combinations, and then the elements are like those clauses that I had mentioned before. They have sort of requirements on the nodes that they exist and that they don't exist. They have requirements on the links. The requirements of the links are specified here. And these requirements are based on transitivity. So the reason that we don't need to write the entire formula is because we rely on this transitivity. Transitivity means that if you have a starting node and the link exists, then by implication, the end node of that link must exist. There is no other choice. So then you don't have to specify the formula, but rather put it in this more abstract form. And then with that formula, we have to do sampling on that formula, but then the sampling gives us a result that is within an epsilon error and with a confidence 1 minus delta guaranteed a priori. So I think that was a major push in our desire to have measurement science brought to engineering reliability simulations. I have some results here. So for grids, let's say just perfect grids, we have done it for power grids as well and such, but just here, the parameter of the grid is n as the side of the grid. So we have grids of size 4 by 4, 6 by 6, up to 10 by 10. We have done other larger ones, but 10 by 10 is a 100 node element that naively you cannot solve. So here we are showing, and we see that the epsilon naught and delta naught, those are the empirical error and confidences, or the confidence is 1 minus delta. So in this case, the confidence is very high. But these are the empirical, the ones that we measure by doing the experiments. Very, very small. We have had to specify errors and confidence much larger for the satisfiability to work. And then the computing time, this is a logarithmic scale. What you see there, that when the probabilities get smaller, our probabilities are specified as 1 over 2 to the power of I being an integer that we keep growing. They start going still exponential. So, but for smaller parameters, they tend to taper. So what happens is we are utilizing tools from the satisfiability world as oracles. We translated our reliability problem from that formula. We create that formula, we lift it in that higher space, and then we call the SAT solver as an oracle. The SAT solver can solve large instances. So instances with small probabilities imply instances with more elements. That's how the things relate. And we call that oracle, solve it, but the oracle eventually will fail on us. It's not a true oracle. It's not that we can just ask the hard question and give us the answer. It's an oracle relative to our field. In that field, tens of thousands of variables. In our field was hundreds. So for querying a 1,000 variable capable solver, it acts as an oracle. But it breaks down eventually. Here I have a comparison actually with one of the most successful methods in other fields. So our method, we call it RelNet. This is the same plot that I had before, the computation time and the error. This is the so-called Karger algorithm. Some of you might have heard. This is from combining graph theory and computation. It does network contraction. It relies on contracting elements. And then in the end, when you have only 2 elements contracted, then if you backtrack the links that form the last superlink, they reflect minimum cuts of the network. And if you count the minimum cuts of the smaller size, minimum cut is the smaller number of elements you need to break so that the network disconnects. Those smaller cut sets are the ones that actually carry the most probability because they are more likely. You have less things to happen simultaneously, so they are more likely. And therefore you can approximate things, and they can also, this is actually so-called, this algorithm is called an FPRAS, a fully polynomial randomized approximation scheme. What it means is that it runs in polynomial time, and it gives you an approximation that is guaranteed. All these guarantees that I mentioned, they are actually within the umbrella of so-called PAC algorithms, probably approximately correct. That you can prove that they are correct within some approximation. So Karger really was a breakthrough early 2000s with his algorithm, but this works only for all terminal reliability. Ours works for K-terminal, which is the generalization. K-terminal can be all, can be source terminal 2, or can be anything in between. So we're still learning, and as I mentioned, for our algorithm to run, we have to specify large errors and a small confidence, but then in practice, we see that the errors are not too great, and the confidence is actually really good. So there is a big gap on what we understand and on the performance of the algorithm. So food for thought, we need more of these sort of logic-based approaches. So one more thing, as I said, this one is still breakdown. You see that the logarithmic scale, time is going to be an issue. If you have very small probabilities, they translate into bigger instances. So eventually for rare event, our instances will exceed the capability of that oracle. SAT solvers that are off the shelf, you can check them. CryptoMiniSat is one of them. And so we then have this sort of alternative. We say, okay, what is the last man standing, or what could be the next step that get us out of the gridlock? So by having expressed our problem as a Boolean logic problem, it happens that there is a direct connection into circuits, like the fault tree is a circuit, or an AND gate, but there is also a direct connection to quantum circuits, which are sort of emerging to exploit the promise of quantum hardware if we get to scale it up. So the idea there is that we endow now every link with a quantum bit or a qubit. So it's an entity that is able to represent a superposition of states. The information is consistent with a superposition, if you want. So every link becomes a qubit. And then the clauses that we played before, they remain logic gates, but they are now quantum logic gates. So this C1 is a quantum OR gate that will take the state of the qubits that are coming in, and given that state, it outputs what the state is going to be. Now the states here, you see that link 6, for instance, it gets that node is a so-called copy operator. You have to actually copy your qubit and entangle it. so that they behave the same when they are both not and both yes, but not in the combination, because that's not allowed, that's not a valid link for our. So that translation is not given to you by the computer scientist or by the quantum physicist. Is the combination, that collaborative where we understand that our links need to be there or not, but not the halfway. For them, halfway is okay because they have been dealing with half spins and whatever. So in any case, so you have basically now, in this specific case, a 6-qubit system, and they are represented by tensors. So a qubit is a tensor, and these gates are tensors. So what you end up is what is called a quantum tensor network. So you have a network of tensors connected by the shared indices that are specified there. And it just happens that that quantum tensor network, since it's an algebraic object, you can ask properties that are algebraic in nature, like eigenvalues or eigenvectors, or you can get traces that they would correspond to averages. So there is a connection in between a quantum tensor network and the lowest energy state of a system. Lowest energy state is where systems tend to go by their own volition. And if we measure something in the lowest level, then we can obtain valuable information. If we measure the ground state of that 6-qubit system, what we get is an answer to the edge cover problem. We cannot get the reliability problem, but we get an answer to the edge cover problem. So here I have, I guess this is just the notation for the quantum state for that 6-qubit. An internal state of this could be a superposition of all 2 to the 6 configurations. The information is not that we have that superposition there, but the information carried by those quantum bits is consistent with that if we measure it. But we can get expectations, and the expectation is going to be the number of edge covers, which, remember, was a problem that was a little bit a relaxed version of the old terminal reliability. So what we realize is that the edge cover is a superset of reliability, and it can provide then a hard bound. It gives us an upper bound on reliability, and it gives us a bound that is exact. And quantum bits, if we have computers with hundreds of them, D-Wave is one of the machines, and has thousands of them, but there are many things on the physical manifestation of them and the error correction that they have and such, but that would be a way to scale up orders of magnitudes to what we were doing. So here are some results. Here in this plot, I have just the time. The dots are our quantum tensor network simulation of a network. In this case, is the grids, again, of size 2, 3, the 10 is a 10 by 10 grid, 100 elements. This red line is utilizing the sort of the RelNet approach, taking that formula, but the easier formula, the one that is local. And it does a little bit, it needs more time. We have these binary decision diagrams, one of the most successful methodologies and it goes exponentially high. And then we have optimal Monte Carlo. These are Monte Carlo techniques that we specify how much simulation you need, again, for some epsilon delta. So all these are epsilon delta techniques. And the tensor network seems to be giving an answer that is faster. And if we show the estimates, obviously our estimates are an upper bound exact. These ones are going to be within epsilon and delta error. So I think with that, I have just the last two things. So here, these results is simulating the quantum system. You can simulate it because there is an understanding of how these superpositions and interferences will occur. But then, what if we want to actually implement on available hardware? So again, having the problem formulated in a Boolean logic is the recipe to express it so that quantum hardware can read it. Because it's so basic. Boolean logic is really, it's like you're feeding the spoonfuls of how you specify the problem. So here is a very, it's a whooping 3-node network. This is using the IBM Quantum Experience. They have it available to the public. You can create your accounts and you can run up to 16 qubits now, maybe 20. So this is just to explain, this is for 3 nodes. If we specify, again, the local problem, the edge cover. So notice that for the quantum, we are doing only the edge cover problem, the sort of relaxed reliability problem. because the reliability problem is non-local, and that seems to require a lot of other things with correlations or entanglement in their field, and part of the research. So we're happy to bring more students on board. Then you need to specify objects that are necessary in quantum physics called Hamiltonians. These are the ones that describes the energy and the dynamics of the system. You need to have an initial state, then you have to have a final state. Initial state could be every, this is actually thinking on the physical object, every spin going up or every spin going left. So that's, you initialize something easily by giving a magnetic field. So you can make everyone point in one direction. So preparing the initial states is easy. Then you have to have an understanding of your final state. So we understand how an edge cover problem should look like, so we can specify how it should look like, and then you do what is called the quantum annealing. You solve the Schrodinger's equation, starting with your easy initialization, and step by step evolving these coefficients so that at the end, after a long time, you end up in the ground state that you care, and then you just do a measurement there, and that would be an answer. The ground state is the space of solutions. So if you measure, you have a solution. That's why the D-Wave and some of these hardware are promising. So we did it for a 12 element network, this grid with 3 by 3 gives 12 links. And T, again, is a discretization time. Here the discretization time from 2, 5, 10, we did up to 100. But you notice that what the curves are giving is as you evolve adiabatically, the probability of finding an actual solution goes up. With 10 steps, we are already very high in the probability of finding a solution. This is actually running the hardware. They are not perfect. There is a lot of errors. If you don't long enough time, you find solutions that are not solutions. So you need to find solutions with high probability, and I think the research is trying to do these error corrections and all that. But then, we went up to 100 and looking at the energy. Remember, the ground state is almost a zero state energy. It's like nothing. So the energy is going in the right direction. So the physics is respected. So I think there is a lot of promise. And so I guess in closing here, I'm just going to have some final remarks. One of the exciting things in the last few years is that these engineering relevant problems are pack computable. They can be probably approximately correctly evaluated, meaning that you just don't give an estimate as we do typically with just Monte Carlo simulation or some heuristic optimization. But we also recognize that the methods that offer guarantees are much more suitable for this future of automated or more AI-driven systems where there is decision making. And obviously the hardware-based part is been exciting. I think it's a tipping point. Maybe people were saying this long ago with the quantum, both information, algorithms, and hardware. But I think it is. I see a lot of research now from NSF. Europe is investing heavily on quantum information sciences, China. So I think there is maybe a time, and in the next decade we will see more. And engineering needs to be there. A lot of the research has been in the fundamental, in particle physics, in chemistry, but groups like ours here, I think, can also contribute because the algorithms are almost co-developed with the hardware. There is a lot of idiosyncratic knowledge that needs to be in so that the solutions reflect real solutions. So with that, I think, oh, this is my cat. Plays dead when I talk about the quantum, so I don't know. It's a joke. Thank you.
I think we have time for some good discussion, so any questions from the...
Yes, Alex.
I saw that in some of the applications that you were looking, sort of increasing the complexity of the program, of the problem description, so that you can have in a domain where even though it's more complex, more variables, it's easier to solve. Because you have new tools available to you. Is that also something that's going to be applied when you're looking at the more detail on the quantum-based, solution to the problem?
That's interesting. I think no. I think the trend has been kind of reducing, mainly because it's expensive to have to require more qubits. So if we go into high dimensional, that means we need more to represent more variables. and therefore more qubits. And at this stage, it seems that the trend is to be as scanned as possible on qubits, because even though we need qubits for computation, then we need many more for error correction and keeping track. So in terms of the realization, I think eventually the techniques, conceptually, I think they will work, but in practice, I think the push is in the other direction to actually demonstrate. Now, what you mentioned, the fact that we lift the problem into a higher dimensional space is because it allows that epsilon delta approximation. So there is very recent work that actually has shown that you can have epsilon delta quantum computations, and they sort of came up, everything is evolving. So they come up with what they call a bubbling operator. And what it does is you start in some part of the system, like in a network. You start in a corner of the network, and you start doing those tensor contractions to swallow the network. But then the key is if you have a specific or an optimal order of swallowing, then you can save a lot of time. But you don't know the optimal order of swallowing unless you fiddle with the problem. So it's more like an online optimization. And I think a lot of that is where I see there is research for. So if that gets solved, I think the lifting will be just normal. Epsilon delta approximation, because many problems cannot be solved even with the quantum computer. So we need to approximate them anyways. Yeah, so that's an answer.
Can I grab on something?
Yeah.
You said you're talking about online optimization, or online optimization. This is, I'm assuming we're talking about like real-time adaptive adjustment to interruption that happen right now. A lot of the computational times that you saw, they're not really amenable for something that is going to be a real-time optimization. Am I right? Or these more type of problems that you do a pre-optimization, a pre-allocation, not necessarily for adaptation in real time?
Yeah, no, that's a good question. The standard ways for dealing, let's say, with infrastructure systems and such, the time scales are days or minutes or hours. But as we move into the automation, we see already a lot of the power grids are getting a little bit more of the automated sort of safe fail mechanisms. And as we push into that, then the time scales are really shortening. And I think we will need then that assistance where we are almost hands-off within the initial steps. Now, we've noticed that optimizers, if you get, sometimes the problem is so hard for the optimizer and for the AI that you just need, the optimizer almost does a best guess, and then you end up correcting for that as you learn more from the system, and the optimizer tries to do the best, given a little bit of history baggage that you have to deal with. But there are some problems for which your initial first steps or moves, they just need to be done. It's better to do something, well, in a fail-safe configuration. But yes, Hassan.
You showed very good examples in the beginning, like NASA or some electric networks, and I mean, all these new techniques are great and should be encouraged to develop. But what level of software or analysis tools they use? Because most of the systems are surviving right now. Are they overbuilt? I mean, over-designed, or why that?
Yeah, no, that's interesting. So for some of the, let's say, optimal power flow, they use standard techniques like I mentioned, some Gurobi, Cplex, things like that. So they are off-the-shelf techniques. What happens is that they are not really getting into this short time step operation. So the power grid, even though most of the time there are failures, the failures tend to be controlled. They tend to be thermal failures, or they tend to be fuses, things that are locally controllable or that have longer time scales. But as we become more interconnected and as high voltage and other renewables start coming in, it seems that the time scales reduce, and you can create then instabilities that are more on the oscillatory nature. That's more like from the electrical engineering side, but those large scale oscillations are the ones that can also create large blackouts. And our structures remain intact, but now it's sort of the operational side. So I think these techniques, we see them as potentially useful in certifying which actions could be taken such that you don't create those oscillations that are out of bound, or that you can control them. So I think that's where we're heading. We are trying to utilize this in some 58 power grids of the US, The results are in a paper that we're going to be posting on the archive. We were talking with. So 58 power grids in the US that go from small networks at the transmission level with 60 nodes to Los Angeles that has 2,000 plus nodes. Houston has like close to 1,000, and we have other. So we are treating now the power grids as a family. They are designed, they look all different, but they should share parameters because they are designed with engineering principles. So what can we learn from applying these things to the family of power transmission networks? So that's on the go, and we hope to gain more insights as we approach the more realistic problem.
I think we're just exactly on the clock, so let's thank our speaker again.
Thank you.